And then over here, it's going to be positives until I get to here, which the slope is 1. So it goes back up and it goes like that. And if you look at that blue function, it's the cosine function. You'll see that? That's a visual proof. It's not a real like solid proof, but you can at least say, yeah, that looks like it could probably be right. So if I graph cosine, there's cosine. So, all right. So pretty close. Thank you, thank you, thank you. So now let me prove it to you algebraically. So I'm going to try and show you right now that the derivative of sine is what? Derivative of sine x is cosine x. Okay, here's how I'm going to do it. I have to go back to the definition. So what would the derivative of f of x be? So we're saying f of x is sine x. What is its derivative? Well, the definition is the limit. H goes to 0. F of x plus h minus f of x. I'm just showing this to you because I want you to see why later on I'm not going to show you a lot of things, because we can get bogged down very seriously in this stuff. If you want to see every proof of every derivative, it would just take too much time. All right, so our function is sine, right? So I'm going to plug x plus h into this, and then plug in x. It doesn't seem that bad right now, right? Limit h goes to 0. We have sine. I plug x plus h into it, and then minus sine x, and then all over h. I mean, that's it. That is how we do the derivative of that using the limit. Y'all see it? The problem with that is that I don't know how I'm going to cancel this h. Because this right here, this h, right, is trapped inside of this sign. I can't like pull it out. So how am I ever going to do some algebra right now to get the h out? Does anyone know what I'm going to do? Anyone seen? How do you mean separate? You could do two fractions. Is that what you mean? Like do this over this, this over this? You could do that. It's not really going to, let me write it. If I do this, I'm going to write, this is algebraically correct. Like there's nothing wrong with you doing this. But the problem is if I let h go to 0, what do I get here still? Division by 0 and division by 0, and there's nothing that actually gets better here, right? Do I have sine junk over junk? No. These junks don't match, do they? All right, so here's what I'm going to do. I'm going to go back to pre-cal, and I'm going to go look in my formula sheet for the formula for that. That's the sum and difference formulas from pre-cal. If you have sine of two things being added together. So what is it? I'd like for you to find it. I mean, I know what it is, but see if you can find it. It's on your sheets. Where does that formula exist? On which reference page? Say again? What reference page are you looking at? Up on top. It says it on top. Reference page 2. And then which one are you using? Yep. Okay. Addition, subtraction. So it's reference page 2, kind of right side, about, what, 3/4 of the way down? So that formula, let me write the formula down just so you have it there. What is it? They use x and y, right? They say sine of x plus y is sine x cosine y plus cosine x sine y, right? That's the formula if we had x plus y. We have x plus h. So just all my y's become h's. I can use that formula, right? So it becomes sine x cosine h plus cosine x sine h. Right? That's what that is. Using that. And then here I have minus sine x still. And then all over h. And when you look at that, you should actually not be very happy because we didn't really do a whole lot other than make it look worse, right? But watch my next move. What I'm going to do, because this is being added and subtracted, I'm just going to move this guy right here, okay? I'm going to go sine x, cosine h, minus sine x, then plus cosine x, sine h, and then all of that over h. So I didn't do anything there except a little bit of algebraic manipulation, right? Just move things around. See where I'm going? I'm now going to split this in, oh, I forgot to put 0 here. Oops. I'm now going to split this into two different limits. So I'm going to do that plus the limit as h goes to 0 of cosine x sine h over h. So I've chosen right here to make two fractions. I did this over h, split it up, and did this over h. Am I allowed to do that with fractions? Yes? If I have the same denominator, I can split it apart? And then the limit, the way the limit works is that if you have addition, you can split it into two limits. So far, does that seem fair to you? Limit, h goes to 0. Both of those have a sine x, don't they? I can factor it out like a GCF. If I factor out sine x, tell me what's still here on top. Cosine h minus 1 over h. So I pulled the sine x out completely and just stuck it right here in front. You'll see it? And then this is plus, look at this one. Limit h goes to 0, cosine x times sine h over h. All I did here is just slid that cosine out in front. I did that so hopefully you would see it. Do you all see it? What happens next? Anybody recognize the limit as h goes to 0 of cosine of h minus 1 over h? It was one of the two important limits I told you to know. What does that go to? This one goes to 0. And then times, it's sine of x, right? Notice the h is not here, right? H has no impact on this. So this is sine of x times 0, which would be 0, right? And then over here, plus, what is limit as h goes to 0 of sine of h over h? This does not have an h in it, right? So that's just cosine x, but this is sine junk over junk, right? The junk matches, and the junk goes to 0. So this goes to 1, and 1 times cosine x is cosine x, and so your final answer is cosine x. That is the proof with using the limit definition. That is the proof that the derivative of sine x is cosine x. And I could do this for all 6 trig functions. I could do it for cosine, take its derivative, and show you what the answer is going to be. I could do it for tangent. I could do it for all of them, right? Yeah. That goes to 0? Yeah. That was one of the two. Do you remember this one? Sine junk over junk is 1? Yeah. Okay. There was a second one that we didn't use as much, but I told you you should know it. That goes to 0. It was cosine x minus 1 over x. If x went to 0, that went to 0.
And it's like the same junk, so it was like minus 1, 0. Okay.
Yep. All right. So are you convinced that the derivative of sine is cosine?
Yes.
Yes? All right. What do you think the derivative of cosine is? Sine would be nice, wouldn't it? It's not, though. It's almost, but it's not. So derivative of sine of x is cosine x. The derivative of cosine x is negative sine x. Not sine x, but negative sine x. Maybe we can, I'm not going to prove this because I think I've already shown you that the proof is, we can do it, but do we want to go through the proof of this one, or no?
I trust you.
Okay, trust me. These are all in your formula sheets, that's right. Let's do this backwards. Which one of these is cosine? The blue, right? So I'm going to make the red one, dotted. And I want us to move along the blue. Right? Where is the derivative? So if we're looking at the blue one, where's the derivative of the blue one? 0. Here, right? So my derivative should go through here. Where else? at pi right here, so my derivative should go through there. And then over here at 2 pi, my derivative should go through there. So that red dotted one looks good, doesn't it? But there's a problem. Look, as I start moving from this point to the right, my derivative is what? Negative, right? And what is my red graph? Positive. And it does this, gets to about -1, and then goes back to 0. So this one goes to +1, then goes back to 0. We need it to go -1, then back to 0. And so all we need to do is take that sine graph and flip it over. And if we flip it, we just put a negative in front of it. And now it does exactly what we want it to do. That's a very loose geometric. Hopefully that makes sense to you why the derivative of cosine is negative sine. Right. What's the next trig function that you know? Sine, cosine, right? What's the next one? Tangent. What's the derivative of tangent? The next 4 are ones that you're just going to take, it's going to take you some time to memorize, all right? I will tell you that, if you want to do well in this class, you need to memorize sine, cosine, tangent as soon as possible. Those 3, get them burned in. Derivative of sine is cosine. That's simple enough, I think. Derivative of cosine is negative sine. I think that's simple enough. Remember, for cosine, it's just off by a sign. Derivative of tangent, just memorize it. Derivative of tangent x is secant squared x. Not going to go through the proof. And then things start getting weird. The derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x is secant x tangent x. Derivative of cotangent x is negative cosecant squared x. Know the first 3, sine, cosine, tangent. Know those, okay? And definitely know that one if you plan on doing well in Cal 2. This comes up a ton in Cal 2. So the others, maybe don't memorize them right away, but try to. They're on your formula sheets. Where are they? Page 5, reference page 5, okay? All right. That's it for the notes, but that's not it in terms of examples. So I want to do a few more examples here.
Is this going to be our test?
Yes?
This part?
Oh,
Like all the rules you just learned?
yeah, everything we did today is, but you have the derivatives there on your formula sheets, right? So you don't need to memorize them technically for Tuesday.
I guess a good question is, will we have our formula sheets on the test?
You're allowed to use them.
Okay.
I don't know if you'll remember to bring them, but remember to. I won't have any extras, so make sure you have them. But you can have your formula sheets, the ones I gave you on the first day of class, right? Those you can have on the test. Anybody not have those? They're on Canvas, so you can print them out yourself. Here's a problem that I tend to get students with. Let's say I give you this. So you have to understand what I'm asking for first, right? I give you y equals that. So that y is a function of x. And this notation means I want what? The derivative, right? I want the derivative of that. That's the Leibniz notation. So I'm going to go try and take my derivative. What do you see happening here? X cubed what? Times. All right, have I shown you any rules on how to deal with multiplication when you take a derivative? No. You can't assume that you can do this and that separately, right? So don't do that. That'll be bad. But you can do what first? Distribute. So before you do any derivative, first distribute the x cubed through the parentheses. So you get x to the 4th, right? Minus 3 what? How do you multiply x cubed times the square root of x? Isn't that x to the half? That's this times this?
Yeah.
Add those exponents? Add them, right? So how many halves do you wind up with? 3. 3.5 is correct, but we need it written in as an improper fraction. What is it? 7 over 2, 7 halves. So all we're doing is doing 3 plus a half there. Getting a common denominator, 6 over 2 plus 1 over 2, 7 over 2. So x to the 7 halves. And plus what? X to the third. Now you can do it. Now you can do it. You can do it. Where's that from?
Adam Sandler movies.
Is it? I don't know. You can do it. Is today the 20th? No, 15th. Oops, I just crossed out the wrong. I just crossed through the whole day, but y'all did a quiz today, so I can take attendance on that.
I believe someone was even late.
Oh, yeah, that's true. All right, can we do derivative now? Each one at a time. Yes? All right, so dy dx equals, all right, I'm going to do these one at a time. I'll show the steps. So I'm going to do derivative of that minus 3 can come for the ride, derivative of this, and then plus the derivative of that, x cubed. Who wants it? What do you got?
So I got 4x to the third.
4x to the third.
Go.
Okay, yeah, sure, if you want.
Minus 21 over 2.
21 over 2, x to the
5 over 2.
5 over 2, good.
Plus 3x squared.
3x squared. All right, so I didn't show work there, but what happened here was the 7 halves came out and hit the 3, and when you multiply 3 times 7 halves, you multiply it like a fraction across. That gives you 21 over 2, and subtracting 1, oops. And then you subtract 1 from this, and you get 5 halves, and then this one is pretty, I think, straightforward. I'm going to leave it like that, and if you're having any trouble, then you can ask me at the end of class, like, how did you get that? That is correct, though. All right, ready for another one? This one gets some students. The next one seems to be trouble for a lot of students as well, at least on this first test. When I give them something like this, x to the third minus 4x minus root x plus 1 over the fourth root of x cubed. I like giving problems like that, or at least one problem like that, and I even tell my students I'm going to give you a problem like that, and then I have students that will struggle with it. This problem is very similar to the last one. Remember we had multiplication, and we could not do multiplication, we couldn't do them individually, right? We had to distribute first. Here we cannot do division, we cannot do top and bottom separately, like derivative of top over derivative of bottom, right? That's you're using a rule that you've made up. You have to do what?
Move it and then distribute.
What do you mean move it?
First, don't you have to do it over bottom?
Move this bottom up to the top, something like that. So I think there's two ways of looking at this, and I'll show you both ways because I know certain students do it one way, certain students do it another way. Here's one approach, okay? This is not the approach I use, but there's nothing wrong with it. And that is to do this. Rewrite it as x to the third minus x to the fourth minus root x plus 1 in parentheses, and then bring this thing up to the top. Now what we mean by that is you rewrite that as a rational exponent, so it should be 3/4 power, right? Isn't that what it means to be 3/4 power? But you brought it up, which means it would be negative 3/4. Is that what you meant? Why am I multiplying? Because I brought this up, right? If I bring it up, it's going to have to be next to this. So that means it's going to be multiplication. And then once I'm there, I can multiply this through like this. And now just use properties of exponents.
Could you also change the x to
Yeah, I'm going to change that to a half. But does anyone have a question on what I did there? That's what you were suggesting, right? All right, so if I do that, let's see. This, and I have not taken a derivative, right? All I'm doing right now is just rewriting the problem. I'll take the derivative once I've simplified everything. So when I put these two together, right, what are you doing there? Adding their exponents?
Yeah.
So this should be x to the 3, I'm adding to that -3/4, right, like that? And I'm going to have to add those. I haven't done it yet. But that's what you do, right?
Yes.
And then you have minus, and then you have 4x to the what? What's the power here? What's the power on this x? 1. So you're going to do 1, you're going to add that. Isn't that how we do it? Some of y'all are looking at me strangely. Isn't that how you do it when you have x to a power times x to the power, you add the powers, right? So that's what we're doing, right? We're doing x to a power times x to a power, add the powers. X to a power times x to a power, add the powers. Just keep the front 1 out front. The next one would be minus x to the half plus -3/4. And finally, plus, well, 1 times this is itself. I've done 0 calculus, right? This is all just algebra at this point. I'm still not ready for the calculus. I'm going to actually clean these up. I've got to figure out what those fractions are. So this I'll put this, let me put it right here. So this becomes x to what? 9/4. 9/4.
Well, -3.
Minus 4x to what? 1/4. X to the -1/4. And then the last one, just leave alone. Anybody disagree? I wasn't even paying attention. I was just writing what you said. Anyone disagree? Did that all look right to you? Looks good to me, yes? Now can I take the derivative? Yes. Because I have something minus something minus something plus something, so I can do them individually, and I can just do power rule on each one. So more fun with fractions now. Here we go. The derivative is, here, 9/4 comes out. X to the, what happens if you subtract 1 from that? 5/4. Yep. Minus, ooh, this is interesting. I have a 4 here, right? It can come for the ride. What happens when 1/4 hits a 4? It just becomes a 1, right? 4 times a 4th cancels out, you just get a 1. So I'm just going to get -1 x to the -3/4, right? -3/4. And then this one, oh, check this one out. Be careful. -1/4 comes out and hits a -1 that's already here, right? So 2 negatives become plus. X to the, careful with that one. A little bit more. You're doing -1/4 and you're taking away 1, which is -1/4 taking away 4/4, so -5/4.
Oh, yeah,
-5/4. Trust me, you'll get way better at this fraction stuff the more problems you do, but you've got to do the problems.
I see. We want to put the 1/4 in front of the x.
Where's that? Oh, did I not put it there? Why did I not put it there? I didn't put it there. Sorry, it was, yeah, sorry, that's my fault. 1/4.
3/4 to the
Yeah, last one, this -3/4 comes out, so -3/4. X to the
-1.
what is it?
Oh, wait, it's
negative 7/4. Negative 7/4, because you're doing negative 3/4, and when you're taking away 1, so minus 4/4, you get negative 7/4. I don't know why this whole thing, every time I go through this part of Cal 1, where I'm doing this like adding and subtracting fractions, I realize like half the class is like, holy shit, I don't know how to add and subtract fractions. And they start freaking out. And it reminds me of this story when I think I was like 10 years old. And my grandfather lived in California. I only met my grandfather on my dad's side like 4 times in my life. We always just lived real far apart. And the man was like a genius, right? He invented cruise control for cars, variable valve timing. Yeah, now when I say he invented it, he never went and actually got his shit patented, which, you know, he should have. But he's one of those people that were just like always tinkering and stuff. So anyways, anyone know what variable valve timing is on an engine? Yeah, a little bit? Okay, so he was tinkering with this idea, and I went to go visit him in California. And this is back when they had like VHS cameras, camcorders, you know, like that's what I actually had in my hand. I was like 9 years old. And he had me go out there into his shop and record him explaining variable valve timing with an engine that was running in a shop no bigger than this room with no exhaust manifold, just like flames and shit flying out. And I'm sitting there like scared, you know, it's loud. And anyway, the part of this story is before we did the video, he was just showing me some things that he was doing on his metal lathe. And he was doing a lot of stuff with fractions, like, okay, we need to subtract 1/32 from, you know, 5/7 and things. He was doing these fractional things, addition, subtraction. And he was doing them in his head, and he would look at me and he would ask me, okay, what's 5/7 minus 1/12? And I'm just sitting there going like, you know, like 9 or 10. He expected me to know it, and I didn't know it. He was very disappointed in me. I look back on it. I do look back on it now, and I'm like, wow, man. He made me feel bad because I didn't know how to do just basic arithmetic. I was 9 years old, and in retrospect, I mean, the reason he could do it is because that's all he ever did. He never used calculators. He had slide rules and shit like that. So his brain was like super fast with fractions. The way I'm doing these fractions right now, it may take you some time to get comfortable with the idea of adding and subtracting fractions. I don't expect that everyone in here can do the addition and subtraction of fractions quickly, but you need to get better at it because you can't be spending 5 minutes figuring out what this is, right? You've got to get to a point where you can do it, and trust me, it'll get there. You'll get there, all right? But put the time in. Some of you obviously have done enough of it, I can tell, just by you're getting the answers right away. So good. If you're not, work on it. It'll get better. All right. He was, he did everything. He worked for the Navy, and so he was doing like stuff on ships and, I don't know. He worked with metal and mostly metal. He's a machinist. There we go. I would call him a machinist. Okay. We got a little bit of time left. I want to look at this review because I want to see if there's anything on here that I have not addressed. So I told you I may not provide you the answers to this, especially if I don't have them already. If I have them, I'll just send them to you. But if I don't, I don't know if I'm going to spend my weekend doing this, but it's 30-something problems. So here, I give you a graph, and you identify all these things, right? So again, this is something that we've gone through. It's not brand new stuff. This we've covered. This is one where I give you all the conditions, and then you draw me the function. We did that in class as well. The rest is just the grind of the limits, right? So the first limit you plug in and see what you get, right? If you get 0 over 0, you're going to do algebra, right? If you get fixed over 0, you know it's one of these things, right? So this is just a bunch of practice. I think the first ones are all algebra, right? Here, 0 over 0, you're going to do some factoring. This one, you see a root? Conjugate. Complex fraction. You're going to put these together, right? Root with fraction. Put them together, then conjugate. That's about as bad as it gets. Let's see, sine 3x over sine 5x, x goes to 0. This was the 0, 0, but this is the one where we had to rip it apart and then be like, oh, I need to put something here and there and slide things over. Students don't like this one. Students don't like this one. I will warn you now that if on a test I give you that problem and you just write equals 3/5, that is correct, but I won't give you any credit. All right? I want to see it. I want to see it come apart. All right? I want to see you actually do the work. Because I could give you a problem where that doesn't work. I'm not going to torture you that way. So I almost want you to know what the answer is. I just want you to get to it. Look at this one right here. If you plug 4 into this, I believe you get 0. Yeah, that's sine junk over junk. That's a tricky one. And then the limits switch to the limits with infinity. Now we're going to infinity. So you get infinity over infinity. What happens when you have infinity over infinity? What do you do? What do you actually do? There's something you're supposed to do. Look at the highest power of the denominator. Try and kill it, right? Try and kill it. So you come in with something on top and bottom here. Anyone know what it is? 1 over x to the 4th over 1 over x to the 4th, and you distribute it through. This one, again, you'll get infinity over infinity, and you do the same thing. This one, you get infinity over infinity, you do the same thing. This one, you get infinity over infinity, but I put a square root in there. That messes things up. I did one like that in class. This one, you get infinity minus infinity. What happens if you get infinity minus infinity? What do you do? Algebra or trick? Do you know the algebra, though? Try and factor. How the hell do you factor that? This one, 14. How do you factor that? Does anyone know how to factor that?
Can you put it in order and take out the highest?
Something like that. If I asked you right now to factor this, like a GCF, did you say? You could do a difference of squares. Yeah, that could work. What would it be, though? What would that difference of squares be? Oh, so you want me to rewrite it? So you want me to go negative and then do x squared minus root x? Is that what you're saying?
Yes, and then x minus x to the 1.
It would be x to the 4th, yes.
And then x plus x.
That would work. I don't disagree with this. And the negatives out front.
Yes.
The only problem I have is that that's still infinity minus infinity. Right? So you still are kind of stuck here. You see? So even though that's correct algebraically, that doesn't quite get you there. You're trying to pull a GCF out. Where's the original? There's the original one, right? Okay, because I want to make sure everyone's on the same page here. This is going to infinity. Infinity minus infinity is something we don't know. So GCF is what we try for. So which of these has the highest power, the higher power? X squared. So this right here has the lowest power. Always try a GCF that has the lowest power. Okay.